Okay, welcome back to this Chapter 4 video. We were in the middle of example 4-21, where we are looking at a skier going down a slope at a 30-degree angle. The coefficient of friction is 0.10, and we want to know what the acceleration is. So in the last video, we created a free body diagram. I talked about how I like to rotate the free body diagram so that the surface of the inclined slope is actually horizontal, and that makes the normal force vertical. And so we set that up and began applying the Newton's second law of motion in the x direction. And that got us this far, but that's about as far as we could go. I guess we could maybe simplify this equation a little bit. Cosine of 60 is 0.5. And gravity is 9.8, so half of 9.8 is 4.9. So this is 4.9 m minus the coefficient of friction was 0.1 Fn equals we can just say ma. We don't know the skier's mass. It was not given. So that's about as far as we can go in the x direction. Let's move on to the y direction now. So if we apply Newton's second law of motion, sum of forces equals mass times acceleration. What are the forces? Well, we have the vertical component of her weight. So we have mg, this time is going to be sine of 60. And we have the normal weight, the normal force going up. This, by the way, is going down. So this is negative mg sine of 60. That's the vertical component of her weight going down, plus the normal force going up. Now, in this case, the skier is not going up in the air or falling down through the ground. She is remaining on this surface. So we can say in the y direction that there is 0 acceleration. So that creates that this whole term then just becomes 0. So now we can rearrange this formula. I'm going to just take this negative term over to the other side, and we can say that the normal force is equal to mg sine of 60, which is equal to 9.8 sine of 60, because that's g, times sine of 60 times m. So that's our normal force. So that's as far as we can go here. But what we can do now is, now that we have this expression for the normal force, we can take this and go back to the previous slide and plug that in right here for the normal force. So now this becomes 4.9 times the mass minus 0.1 times, let's see, what was that expression? 9.8 sine of 60 m. 9.8 sine of 60 m. And that equals m times a, acceleration. Now, you may have thought at some point in time, maybe when we got here to this point, or when we got here to this one, thinking, gosh, I don't know if we can solve this problem without knowing the mass. Don't we need to know what the skier's mass is? because we've got an m there, that's unknown. If we jump back here, we've got another m here, that's unknown, and an m here. But by combining these two equations together in the x and y directions, what we find is we have this term, it's got an m in it. We have this term, that's got an m in it. And we have this term, that also has an m in it. So what we can do is just divide all of these terms by m and just get rid of that term. Just falls right out of the equation. So that now just becomes 4.9 minus 0.1 times 9.8 sine of 60 equals acceleration. And acceleration is what we're trying to find here. So if we calculate this, 4.9 minus 0.1 times 9.8 sine of 60, let's put that into the calculator, I get 4.05 meters per second squared. And that's it. That's the answer. That's what we were looking for, is what is the acceleration downhill. So as it turns out, interesting thing to note here, it doesn't matter what the mass is. It doesn't matter if you have a very small, petite skier or a very large, massive skier. According to physics, the acceleration will be the same either way. Now, in the real world, you do have to keep in mind there are some other variables such as wind resistance. So I suppose a larger body would encounter more wind resistance, so maybe it is more beneficial to be a smaller size. But there's also some physical acceleration that the skier does at the top of the hill. So it's a balance, I suppose. But from a purely physics point of view, mass is irrelevant. So that's kind of a fascinating side note, I think. Okay, so that finally brings us to the end of Chapter 4. It's a bit longer than some of the other ones, a lot of example problems in these videos. So that covers Newton's laws of motion. We're probably going to continue to refer to these laws. It comes up quite a bit throughout the rest of the semester. So hopefully you'll have a good, firm grasp of Newton's laws. And again, I encourage you to use the discussion board if you've got any questions. And that's it for Chapter 4.